Okay, so I'm very pleased to be here again amongst all these famous and very eminent neuroscientists. I do regret not being in Rome. I was really inclined to go there, but unfortunately I couldn't, so I have to deliver it online. My background is actually not neuroscience. I'm a management person, although I've been working for 2 decades on neuroscience and biometrics because I had the lucky happening of having doctoral students, neuroscientists, working neuroscientists, and I've done a lot of research collecting knowledge for hospitals. But mostly nowadays I'm talking about, neurotechnologies for the future and about neuroscience in terms of theory. So related to the future, my talk will be about futurely to be seen brain advances. And I'll be talking in terms of brain-computer interfaces, robotics, mind uploading, all sorts of reverse engineering, neuromorphic computing, very, very important, related to quantum brain, and all sorts of biocompatible technology, and how this will actually impact on humanity. Are we going to have an augmented humanity? Are we going to have humans 2.0, cyborgs, etc.? So I'll be talking about the future and the development of neurotechnologies. Obviously, the starting point is about BCIs, brain-computer interfaces, which is mostly...
Doctor, sorry for the interruption. And please open your modes in a presentation. The modo apresentação do PowerPoint.
You're talking about... Okay, fine. Is it okay now?
Perfect. Thank you.
Okay. So BCIs, as you all know, is a neural prosthesis, any technology linking the human brain to a computer. More and more, we've got all sorts of computational systems which are implanted in the brain, will allow a human being, a person, to control a computer using only brain waves. Either, by reading electrical signals from the brain, a person can focus on a computer screen. And this actually is using nowadays for more repairing cognition, human cognitive functions, sensory motor functions, etc. There are all sorts of mind control robotics as well, based on this BCI, from very easy ones, very inexpensive ones like MindWave, Neurosky, but they're all related to detecting brain waves and transmitting signals over Bluetooth or translating patterns of brain activity, also using biofeedback. An example of this is that you can have a mental task. You have a protocol based on ERPs. So a brain responds to as a direct result of a specific sensory event, cognitive event, motor event. And then, of course, you have the amplifier and the conversion between the mental task and the algorithm. And through signal processing and feature extraction, you can actually have this BCI. So what's happening in the future? Are we going to have 24/7 connectivity to the internet? Maybe the BCI functionality of typing on a keyboard, just with the mind, suggests that we have a lot of possibilities of having always these brain internet connections. Again, human cognitive processing can also be linked not only in terms of internet through BCIs, but also virtual reality headsets, and even quantified self-wearables, etc., even smart contact lenses. So mind uploading is coming upstream nowadays. We're talking about transferring human consciousness into a non-biological carrier. These can be personality traits, emotional details, memories, and maybe this could be immortalized as well. So creating these digital forms of humans is, will have a lot of impacts and ramifications, and this could actually upset the usual cycle of society, economies, etc., our lives. There are some dangers. Digital minds will be, theoretically speaking, free from biological threats such as toxins, but will be open to new risks. For instance, can it be exposed to malicious hacking, reprogramming, surveillance, and even being copied against the will of the person? So are we going to have a new society? On one side, we've got emulations. On the other side, we've got human intelligence, so as a template. So again, what the humans, the biological humans, is a kind of a gathering space for knowledge, for experience, for resources. Whereas, are we going to be pushed towards the periphery of the society? I don't think so, but it's incredible, this divide between emulations, technology developments, and the human intelligence. So mind uploading would cause certainly a number of changes. A lot of advances in terms of AI, artificial intelligence, computing, neuroscience. But maybe the boundary between biological and technological will more and more become blurry and will blend. So we're talking about biological engineering. So more and more we're talking about smaller. We're talking about miniaturization, and we're talking about wearable technology, but also 3D printing, augmented and additive manufacturing. So 3D printing, which now we're talking about 4D printing, tesseracts, and very soon up to 8D printing. So this can help us to deliver medicines in vivo, in also sensors for brain control prosthetics. We can create microneedles for drug delivery. Incredible. So all these bioprinting, three-dimensional printing as well, will be integral to creating human organs and producing this new biological engineering era. Incredible. The possibilities in terms of these developments. And also nanobots. Nanobots, within the next 5 years, they will go into a brain and non-invasively through the capillaries or through your arteries and connected to our neocortex. De facto connected with the synthetic neocortex, the same way in the cloud. So the cortex, which is really, as you know, the cerebral cortex, half of the volume of human brain, which deals with attention, thought, perception. Incredible how these nanobots can actually go inside. So nanorobotics is an incredible intersection between neuroscience and robotics. An emerging area of research, and what we're trying to do is to how can we find and use controlled robots using neuro-inspired technologies for functional abstractions in areas, a lot of brain models, anatomical areas of the brain, which can actually be developed into brain models. So incredible, because at the same time, this neurorobotics can actually create an area for explore how ethical issues, how social concerns relate to our scientific research. Incredible. Neurobots, are based on control. They are modeled about some particular aspect of the brain, and the brain that is closely coupled with the body, but also with the environment. And neurorobotics can be a very powerful tool to study these neural functions in a very holistic fashion. Incredible. And also can actually help us to develop autonomous systems at some level, based on some level of biological intelligence. We have already an advent of SAS, symbiotic autonomous systems appearing on stream, appearing on the landscape. So neurorobotics is very important. It's a very powerful tool for testing theories of the brain and increasing our understanding of what is neuroscience. Interesting because the control of the robot itself, obviously modeled about, in terms of the nervous system, but it is interesting because the neurorobot can actually have access to every aspect of the artificial brain during the lifetime of the agent. Therefore, the neurorobot can analyze, can even influence the nervous system in ways that the present recording technology cannot at the moment, despite the huge advances in terms of this imaging technology. So we can also test neurorobots under lab conditions, but also in terms of real-world situations. But interesting enough, we need to make sure that we are adapting to a changing environment. A neurorobot must be able to learn, must be able to store, must be able to recall information. So the issue about spatial and contextual memory is paramount. So memory systems in neurorobotics are especially applicable in spatial memory for navigation and also the contextual memory for learning representations of the environment. Nanobots will be flowing through your body, through your arteries, probably in about 5 years, towards the end of this decade, to navigating, injecting through your bloodstream. And this probably will prevent you from getting sick, or you can even transmit your thoughts to a wireless cloud. These are strands of DNA robots which have the capability of moving throughout, inside the bloodstream and injecting blood clotting drugs into blood vessels around, for instance, tumors, cutting off their blood supply. Nanobots will then therefore be able to assess and fix us from within. So our own of our own DNA will eventually cure us and human beings from deadly disease ranging from blocked arteries to cancer. And this will give, as a springboard to have more regenerative medicine. Of course, we have the ethics debate which come into play by helping everyone getting access to clonable organs. Is that right? Is not right? People have this debate, and the medical ethics has to come to play an important role. And we might even create a human body 2.0, 3.0. We might even redesign, for instance, the digestive system is rebuilt. We can have, via clothing, we can have auto-nourishment, and nanobots can go in and out of the skin, cycling nutrients. And also the digestive system and the blood-based nanobots can actually supply these precise nutrients. We can even redesign parts of our body. We can have obsolete organs, and nanobots can deliver oxygen to the cells. So in the future, we'll link the brains with artificial intelligence system more and more. We might have infallible memory. We might have brain-to-brain communication. We might see even body extensions in objects located hundreds of miles away. Or even we might get also multidimensional thinking. All that is part of reverse engineering. So reverse engineering of the brain. How can we repair? How can we educate? How can we augment our own mind? So the race is on, and reverse engineering will continue to provide a very faster route to link to real artificial intelligence. So, something that forward engineering ignores is the brain. So we have more and more of these digital interfaces and neural interfaces creating bionic humans. We can have, and we are already developing artificial synapses. So successful interface between neural and digital, we can have a strong connection between the electronic and the biological. And this interface nowadays, we are talking about not just having two adjacent neurons that usually communicate via chemical neurotransmitters across a synaptic opening, and we are developing an artificial replica of a synapse that allows the device to integrate and to interact with living cells electrochemically. And of course, the connectome, the totality of connections between neurons in the nervous systems. We talked about a connectome, the human connectome, this comprehensive map on neural connections in the brain, a kind of a wiring, a diagram of neural pathways. Incredible, because these neural connections in the brain, the connectome, is actually mainly represents molecular connections between neurons, and trading on the analogy of almost like an electronic device with axons, with dendrites, etc., as wires, but also with neuron bodies as components. Another important element is really the issue about neuromorphic computation and quantum computing. Neuromorphic computation attempts to imitate the human brain, how the human brain works. Hardware, software, elements of a computer are then wired to mimic, to emulate, to replicate the human nervous systems and the human cerebral system. So the goal of neuromorphic computation is to create devices that can learn, can retain information, and can also make logical deductions, just like a human brain does, without trying then to imitate the human brain by searching for new information. Whereas quantum computing is completely different because it deals with the world of atoms and subatomic particles inside those atoms. So unlike neuromorphic computing, quantum computing works on the principles of entanglement. There are other properties, but entanglement is one of the most important ones. And of course, the smaller the computer gets, the much more powerful they seem to become. So neuromorphic computing, incredible, is copying the methods of human brain, how the human brain functions, closely related to computing engineering, and of course, including software and hardware. And again, and these are equipped as per like the human cerebral system and the human nervous system, as I just told you. And this gives rise to a much more complex element, which, if you want to link with artificial intelligence, then the computer requires the understanding the patterns in the surroundings and also to learn new patterns. So the quantum brain comes into play, which is the main instance of neuromorphic computing. Also the future of computing. This incredible, the quantum brain, will have the help of what we call cobalt atoms on a superconducting black phosphorus surface to copy the methods of signals in the human brain. So these cobalt atoms consist of quantum properties such as, for instance, unique spin states which process information in the same manner as the brain. So again, the atoms then will allow us to accomplish a self-adaptive behavior depending on the stimuli from the environment that we get. So we are talking about biocompatible technology, small in-brain computer chips. We all know about Elon Musk and what Neuralink did with the first brain implant, called telepathy. But are we going to have more and more? Yes, future implants, they're going to be more and more built. So stimulating the brain externally with electronic signals is already being experimented by in a number of fields, by institutions, etc. You know that the human body, when we get artificial devices in other parts of the human body, we have a lot of, most of them without any rejection by the immune system. The brain is still pretty much an unexplored frontier, but we will see. So this biocompatible technology will understand the process of the human brain, and we'll be looking at a number of applications in medicine in the future. Also, the DBS, deep brain stimulation as well, the brain implants can actually help, for instance, in terms of depression. If we actually target a small part of the brain structure, area 25, for the brain circuits that control our moods, the moods of human beings, and electrodes can reset the mood from being sad to being normal again. Again, an application of a brain implant. This neurotechnology will enable us or users to interact with the environment and even to interact with other peoples by thought alone. Incredible. And to have the power of moving scenes. Incredible. One of the most popular branches of neurotechnology in terms of a link with the BCI is how can we control electronic devices just by thinking, either be a game or a computer or a drone. And these devices consist of mainly electroencephalography sensors that capture brain activity. Then the data is processed through an artificial intelligence model or several models using deep learning, artificial neural networks to extract the main features. Then the features are matched with specific commands to move the object. Again, incredible. We can have mental control, and this can become more and more of a reality. You can even paint. You can paint. You can have, if you want, if you are inclined to do some painting, you can actually use recording EEG signals through an amplifier. You can process the signal. So after you actually have some stimulation, visual stimulation, through your focus attention, you can actually select, so there's a detection of user selection and apply to whatever you are doing in terms of oil painting. Incredible. And there's a lot of applications in terms of brain-computer interfaces. You might even, if your head of department wants to make sure that you are actually paying attention to your Zoom meeting at this conference, you can actually do that through brain-computer interaction. You can actually prepare your next presentation for your next conference just using your thoughts. And these scenarios are becoming a reality, transforming our future through brain computer interaction. And this will give rise to what we call augmented humanity. So this human computer integration technology is increasing capacity, productivity, and also changing our normal range of our functions, human functions, through not only the restoration of human, but also intellectual and physical and social capabilities. So are we going to reach the point of having supernatural abilities? Some of us dreamed about that, the obsession about superheroes, etc. But de facto, we are now developing some devices to allow humans to see the infrared spectrum, to feel magnetic fields and sound vibrations, to enhance and improve our memory, to improve our endurance. So we are pushing the boundaries of what is possible. How much? We'll have to wait and see. And upgrading ourselves. More and more, we are linking our brains with artificial intelligence systems. And this will communicate in all new ways, a new world around us. We'll be able to understand this more complex world, to understand it in more, based on more dimensions, which is an advantage of AI. So the future, human 2.0, yes, we can have bionic eyes to see the infrared spectrum. We can have even artificial skin to allow us to feel magnetic fields, to sound wave vibrations, and we can have a brain implant to improve your human memory. You can have an exosuit as well, a portable exosuit to allow us to have more human endurance. Incredible, all these scenarios for the future. Can people be reincarnated through artificial intelligence? We have to wait and see. Most of us won't be around, but anyway. But if you recall what Professor Noah Harari said, we're going to have as well godlike cyborgs as well appearing on the street. I don't think actually we need to wait 2 centuries. We've got already a cyborg future. Many of us rely on bionic ears, eyes. We're actually using insulin pump technology, prosthetics to help us survive. So again, we can send our thoughts across the web. We can subconsciously control bionic limbs. We can use even liquid metal to heal severed nerves. Again, yes, are we going to have cyborgs in the near future? I guess so. Look at that. This will brain look like in terms of the physical part of the brain, with all these electrodes, etc. So, de facto, what we are doing is actually emulating human brain. And we can do that by having cognitive architectures. So, innate to intelligent, to an intelligent system of work inspired by human psychology, is the human brain is not really just, a human brain is not a homogeneous set of neurons. There is a real structure in terms of different components. Some of them might be associated with knowledge, how to do things in the world, which is procedural memory. Others might be knowledge based on general facts, semantic memory. Others must be knowledge about previous experience, episodic memory, etc. So brain architecture ultimately will combine, work together genes and experiences to construct a new brain architecture, a cognitive architecture. So theories of cognition, we try to capture the essential representation that underlie are behind cognition. So a lot of research is going on cognitive architectures that gradually move from just looking at the functional capabilities of the cognitive structure, but the ability to model the details of human behavior and more the details of brain activity. So cognitive architecture, very important. What are the main differences between a brain and a machine? While the brain is learning from very little data or examples or creating solutions, sometimes to problems that are not very well defined through deployment of attention, metacognition, concept formation, memory, The machines cannot match these capabilities of the human brain, but they are able to perform at a high level in many other tasks, for instance, perception. So interesting enough, I mean, we're looking at artificial intelligence a number of ways. The first wave was, when I started working on expert systems, we had the programming, and then we moved on to a more recent wave, second wave, based on machine learning, deep learning, artificial neural networks, etc. And of course, this third wave that now is appearing is based on cognition-based artificial intelligence, with the cognitive architectures that really comprise capabilities of perception, attention, learning, action, memory, reasoning. And this is much more difficult, challenging, but it's very important because it will give us a huge reward in the future, and also is inspired in neuroscience. And also we are getting closer to augmented, to general artificial intelligence, which some appear, 2045, 2040. Even now, some experts are saying we might have, general artificial intelligence to will be able to solve any problem, not just a specific problem, by the end of this decade. Neurosymbolic artificial intelligence, therefore, also is actually using nowadays more and more this agentic AI, intelligent agents that will embody a myriad of artificial intelligence tool, neural networks to represent knowledge, to use abstract reasoning, and more and more people we are trying to develop a standard model of the mind using artificial intelligence, cognitive science, neuroscience, and also robotics. And for that, it's interesting because nowadays we're talking about an integrated cognitive architecture, and we are not just like artificial intelligence. We want less reliance on trial and error. We want less reliance on using large language models, large amounts of data, zettabytes, yottabytes of data and experience. We want to being able to incorporate innate knowledge and common sense. And there are a number of areas which are very important in terms of providing this contextual meaning. So interaction networks, neurophysics engines, and recursive cortical networks are some of these examples. So again, how can we emulate the architecture, the operation of the brain, by designing these cognitive architectures, also addressing problems like cognitive problems, visual motor problems. We can do that through simulations. We can do that by using virtual or real robots, by studying all these interactions, closed loop interaction between the brain, the body, and the physical environment. So again, we should target a new cognitive framework by having this range of heterogeneous modules representing different brain areas and creating new rules, learning rules to train the modules in biological plausible ways, and of course using neuromorphic computing for energy efficiency, and of course to be able to perform a variety of cognitive functions, and more and more to also test hypotheses about brain functions. Again, neuromorphic computing is very important because not only the human brain is based on the human brain, is very good as storing, processing information, but of course we are trying to develop now computer technology that mimic how neurons operate in the brain. And sometimes as well we are concerned about how these can be energy efficient. Yes, neuromorphic computation, neuromorphic systems can deliver that improved energy efficiency as well. And we are approaching singularity. Again, end of this decade, 2040, 2045, exponential rate of technological progress, incredible. This singularity might allow us to have enhanced human intelligence, to magnify our creativity, and we are entering a new evolutionary stage of mankind, a new epoch for the cosmos. Ray Kurzweil from Google, a very famous futurist in this area, predicts that maybe by around 2040 we'll reach the singularity. Technological singularity, but singularity as a whole. So computation in artificial intelligence will be smarter than human intelligence, and it will exist to replicate and to enhance itself already. We're talking about 20 years from now. So It's a new epoch. If we started from the beginning, these epochs, the physics, the chemistry of the universe, the carbon-based compounds, life then emerged, and then we talked about the human brain. But now we are entering a new epochal moment. In this next leap of the universe, we're talking about the merger of humans and technology. It is the age of bionics. So the machines will make this transcendent human brain limitations of mere 100 trillion extremely slow connections to overcome age-old human problems and vastly amplify, as I mentioned, creativity. Incredible. It's a new stage of humanity with silicon in our brains and titanium in our bodies. And again, he mentioned about that. I mean, probably very soon we'll be passing the Turing test by the end of this decade. And of course, singularity will come into play in 2040, 45, 40. This leads computers having human intelligence, putting as well, or putting them inside our brains. Incredible. So what is actually happening is machines are powering all of us. They are making us smarter. They may not yet be inside our bodies, but by the end of this decade, it will connect our neocortex, the part of our brain where most of our thinking takes place, to the cloud. We talk about reverse engineering, therefore, reversing engineering of the human brain by using these supercomputers, very powerful supercomputings. Again, computing architectures to amplify and processing capabilities. This will be actually create the ultimate machine that help us handle a lot of challenges in the future. So for a number of years nowadays, neuroscientists, computer engineers and psychologists have been trying to simulate human brain so they can ultimately create a computing architecture based on how our mind actually works. This is actually based on reverse engineering of the human brain, decoding and simulating the cerebral cortex, which is the seat of cognition. And the human cortex is about, 22 billion neurons, 220 trillion synapses, etc. Incredible. So you want more counts, we can have more counts. So this reverse engineering in the brain is based on genome. The human genome has about 3 billion base pairs, or if you will, 6 billion bits, which is about 800 million bytes before compression. If you want to apply lossless compression, that information can be compressed into about 15 million bytes. But half of that is the brain, which comes down to about 25 million bytes, a million lines of code. But it's whatever happens, will not happen. Anything, perfect simulation will not happen unless it is infused, if we are integrating knowledge and training. So our enhanced technology, yes, I believe that the world of enhanced intelligence will appear, in which probably we might see a 20% increase in intelligence. And more, we'll have a synthesis, a human-machine synthesis. Instead of machines taking over the world, as some people say, that's not the right visions of of singularity, but will be a future of unparalleled human-machine synthesis, integration. Think about, through the problem of human-machine collaboration is one of the most vulnerable cases, opening our brains up to big data, to brain-computer interfaces, cloud minds, cloud-based thinking collaborations. Incredible. So replica of the brain, a human-like computer brain is a matter of time. Yes, will appear with about 100 billion nerve cells, each of which is connected to another 10,000 or so neurons. The natural neural network inside our heads is a very complex thing. But, the ability to process many stimuli and signals in parallel is pretty much still underdeveloped in terms of computation. But there is, examples of brain-inspired hardware. So examples of human brain-inspired hardware for artificial intelligence. So, for instance, one of the interesting things is the putting tens of thousands of artificial brain synapses, or if you will call memristors, memory transistors, into one chip that is smaller than one piece of confetti. These are silicon-based components that replicate, that emulate, that mimic the information transmitting synapses of the human brain, the so-called brain on a chip. We might see this in the future. Currently, also people in the States, people in Hong Kong are also creating models for it to simulate human learning. how can we actually simulate to learn by association via the synaptic transistors that process and that store information at the same time. And that's it. Thank you very much for being there. This is only a joke. You know what gets into my nerves? Myelin. Thank you so much for being there.